In Essential Task 8.9, we are going to discuss aspects of sleeping, including talking about the sleep cycle and each of the distinct stages within your sleep cycle. The concept map from afar looks a little unusual, but it's actually structured quite traditionally. There's two boxes here at the top, sleeping and then the awake/sleep cycle. On this final level, you will find the bulk of today's concept map, which is a single box on the left labeled awake, and then two columns within this region labeled sleep cycle. So I know when you look at this from afar, it looks really intimidating, but in terms of your concept map, this is really a 3-column last level. We're going to do a graph visual of this sleep cycle outside of the concept map, so you don't have to try and replicate the color coding, what you see going on here. It's a little bit intimidating to try and do. So in terms of the actual concept map itself, there are two boxes at the top, sleeping and the sleep cycle here. And then on the last third level, there are 3 columns worth of information. Though I will say this second column here has a reasonable amount of text. So do make sure you have enough space here at the bottom for the entirety of the second box on the third level. But as a whole, what you see under sleeping is the entirety of today's concept map. You might notice the topic sleep disorders off to the right, but that is the topic that we'll get into in 8.10. So I'll bring you back now to the task text. It's short, just discuss aspects of sleeping, but I'll allow you to pause the video here before proceeding into the concept map. Sleep might seem like an unusual word to define. It's a word that we're all quite familiar with on a personal level, but there's some elements of the definition of sleep that I think are important. The first is that when we sleep, we go through 90-minute cycles. Within the 90-minute cycle are 4 distinct sleep stages that you may or may not, depending on how long you've been sleeping, pass through. And if you were to wear an EEG, which is the most common way of evaluating sleep, we would be able to determine which of those distinct stages you happen to be in at each point in your night's sleep. Beyond just the 90-minute cycles and the 4 distinct stages, and again, we use an EEG, the most common way of evaluating sleep. In addition to that, there are some things that influence the extent of our sleep in terms of length and also quality of sleep. First is age. Older people actually sleep less because more often than not, their sleep is interrupted. Older people tend to wake up in the middle of the night more frequently, and as a result, they do not typically get the full 7-8 hours of uninterrupted sleep that you might get when you're younger. This might seem a little unusual to people, but when you take into consideration the quality of the sleep and you look at it in terms of a full night's sleep, older people do typically sleep less than younger people. If you're familiar with somebody who's much younger, you might realize you put them to sleep at 8 o'clock, 9 o'clock at night, there's a pretty reasonable chance that they'll get at least 8 hours of sleep, if not longer, if you were to allow them. So age is one variable that determines the extent to which you would sleep if given the opportunity to sleep. There's also sort of that asterisk here that, yes, younger people might have to go to school or have jobs relative to individuals who are retired. So there are some environmental things, but if individuals are given the opportunity to sleep to the extent at which they would sleep normally, older people would sleep less. The second is genetics. What we find is that each individual person has their own quantity of sleep that might be necessary for them to perform at their peak. And it can vary by an hour here, an hour there. However, individuals that are identical twins with the exact same genetics tend to have very similar sleep patterns and sleep schedules, more so than fraternal twins, and definitely more so than unrelated individuals or even just regular siblings. So in addition to age, we've also found that genetics seems to impact how long our body would like to sleep if given the opportunity to sleep. The third is identifying changes that are cultural and time-based. One of the biggest changes is in modern lighting. At one point in time, you needed candles to light your room at night. Now we have the ability to totally illuminate our room almost as if it's the middle of the day by turning on lights. People work shifts that are much later now. At one point in our human history, there really wasn't a such thing as a night shift because we didn't have any of the indoor lighting. Modern technology has also given us the iPhone, which for many of you realize can be incredibly distracting in the middle of the night when you're trying to go to sleep, because next thing you know, you're taking your phone and flashing this bright light into your face. Well, that's going to make you stay awake a little bit longer. That's going to interrupt your overall sleep schedule. So in addition to just age and genetics, there's also cultural environmental shifts, whether that's modern lighting or technology as a whole, that directly influence the extent to which we sleep, both in terms of quality and quantity. The next thing to do is determine and reference what's called our awake sleep cycle and talk about one of the most commonly cited terms on the AP exam called the circadian rhythms. This term circadian rhythm is The more technical term for what people typically call the biological clock, I imagine many of you can relate to the idea of going to sleep, forgetting to set an alarm clock, but then waking up relatively close to the time that you needed to wake up, maybe within 20 or 30 minutes, and still being able to get to work or to school on time, even though you forgot to set an actual alarm clock. In the back of your mind, you're like, oh, luckily my biological clock woke me up on time. Well, the more technical term for that would be your circadian rhythm, because it is true. There is an approximately 24-hour cycle of changes that occur related to body temperature, hormone releases, and a variety of other changes that does in fact regulate our sleep-wake cycle. There are points of a 24-hour period of time where our body tries to put you to sleep. Even if you need to stay up late to do work, even if you need to stay up late to get an assignment in by midnight, there is a point of the night where your body is going to begin to undergo changes in body temperature and hormone levels that is going to try to put you to sleep. And it's going to do that at basically the same time every night. And then on the tail end of that, it's going to shift and alter those changes, increasing body temperature, for example, trying to wake you up in the morning at approximately the same time. So eventually, when you have a solidified biological clock or circadian rhythm, yeah, you very reliably will wake up even without an alarm clock, because your body is just naturally going to wake you up at these points. Many individuals can probably relate to waking up at 6, 7 o'clock in the morning during a vacation week, at least at the beginning of the vacation week, because your body has this really set in stone circadian rhythm that it's still going to follow regardless of if you actually have to go to school that day. This influences the sleep-wake cycle, and it is primarily influenced as a result of melatonin changes. Melatonin is a hormone that we referenced in the previous essential task, but it is secreted as a means of regulating the sleep-wake cycle. So we see increases in our melatonin levels when we, in theory, should be going to sleep, at least when our body wants to put you to sleep, and then shifts in our melatonin level in the morning when we should be waking up. If you've ever experienced what's called jet lag, which typically occurs when we change time zones, it has to do with the fact that our circadian rhythms are not sensitive to the environmental changes that occur in the context of time zones. When you go to California and you're 3 hours behind, your body still wants to put you to sleep at what might be 10 Eastern Standard Time, but that's 7 o'clock Pacific Time. And those quick changes that you go when you travel across the country significantly disrupt your circadian rhythms, and it makes it so that you can sometimes feel incredibly jet lagged or just overall exhausted, because the time zone that you're currently trying to live in does not match the time zone that your body developed the original biological clock or circadian rhythm within. It's very common to see this term on the AP exam in the context of an FRQ. Oftentimes it might ask, how can a circadian rhythm hinder your ability to perform something? And if you related it to travel and a shift in your circadian rhythm as a whole, you very likely could score that bullet. The third tier, the third level of today's concept map, is to talk about particularly brain activity in the context of being awake or asleep, but talking about what our brain looks like when we're awake but relaxed, and then transitioning into actually talking about what our brain looks like when it is sleeping. Again, the second box here in the middle is a little bit taller than any of the others on this level. It's the one here that certainly is going to necessitate the most space. When we are what we call awake but alert, which would be the equivalent of meditating or relaxing, or maybe even technically dozing off in maybe a class or at work without actually falling asleep, if we were to hook up an EEG, attach a bunch of electrodes to the scalp of your head, we would see that you were exhibiting what are called alpha waves. It's a term that we use to reference the level of brain activity. When you're relaxed, you're drowsy, but you are technically still awake. So this could be anything from just closing your eyes in class when you feel like you're getting tired, or closing your eyes at work when you feel like you're getting tired, closing your eyes at home when you tell yourself, all right, I'm not going to fall asleep, but I am going to close my eyes, or even when you are meditating. We call those alpha waves if we were to actually look at the overall degree of brain activity. We're going to compare and contrast alpha waves to the type of brain activity that is exhibited when you're in deep sleep in just a few moments. But as a mnemonic, I look at the letter A, and if you look at the letter A, particularly a capital A, it always reminds me of somebody who's meditating. Just that perfectly symmetrical peak there reminds me of somebody who's sitting down and meditating. And if you could connect alpha waves to meditation, that would be a sufficient way to connect when alpha waves would be exhibited on an EEG. Not when you're awake and alert taking a math test, absolutely not, but when you're awake but relaxed. And now we'll start talking about the sleep cycle. Don't get intimidated by the visual here. I'm only asking you to do the 2 columns. The actual visual itself is something that we're going to use for classwork, so don't fret trying to copy down this entire graph. We'll talk all about this chart and this graph in just a few moments, but we're going to get into the content of the 2 columns remaining. The first column is going to talk about The first three stages of our sleep cycle, NREM 1, NREM 2, and NREM 3, this isolated column, this isolated box to the right, we'll talk about what's called rapid eye movement, or REM sleep. First, let's talk about stage 1, non-rapid eye movement 1. This is the very first stage that you enter when you go to sleep, and it's technically only the first 10 or so minutes of a night's sleep. This is the stage of sleep where you are technically sleeping, but you still have some degree of alertness. Your body hasn't really fully entered into some of the stages where the brain activity drops to a really low quantity. And as a result, it's very easy for somebody to wake you up when you're in NREM 1. Someone could open a door, somebody could put something down, somebody could do something in your environment, and it could be very easy for you to wake up from NREM 1. Chances are, if you've ever actually fallen asleep at school, technically got to the point of truly sleeping, you're in NREM 1. So something occurred in this classroom that probably woke you up very quickly and abruptly. If you enter into NREM 1, you are technically sleeping. You're no longer in that awake but relaxed state. No longer. We are now technically sleeping. One of the unique features of NREM 1 are called hypnagogic sensations. These are what we call sudden awakenings, often accompanied by the feeling of falling. Have you ever had the sensation where you're relaxing on the couch and then all of a sudden you feel like you're falling off of the couch, or you're in your bed and you're really planning on going to sleep, but you dozed off, then you sort of jolt up? That sensation of falling is a very specific element of NREM 1. It means, yes, you did doze off, you were technically sleeping, and as your muscles began to relax, it triggered this weird sudden awakening feeling. That's what triggers that sensation of falling. It has to do with the muscle relaxation that occurs during that first 10-minute span when we first go to sleep. Now, what's important here is this is only the first 10 minutes. So you're going to notice that I have this chart color-coded. You'll notice there are technically 4 colors. There's white, red, dark green, and then a light green. This white region here, labeled NREM 1, never occurs again through the entirety of a night's sleep. So that's only the first 10 minutes. NREM 1 will not repeat at any point for the duration of a night's sleep. We are now going to transition from NREM 1, and the numbers work pretty easily here. We're going to go to NREM 2. Non-rapid eye movement stage 2 is your baseline sleep, in the sense that you spend approximately 50% of one night's sleep in NREM 2, which means if you go to sleep for 8 hours, you'll sleep approximately 4 of those hours in NREM 2. And we'll talk about why that is the case when I zoom out and show you what this looks like when we compare a full 90-minute cycle. So you actually do NREM 2 twice within one cycle. The biggest feature of NREM 2 are the presence of what are called sleep spindles. If you were to look at EEG findings or results, which is what is indicated in the visual here, these little moments where the red arrow is pointing at the increase in amplitude and frequency are examples of sleep spindles. So there's a big burst of brain activity here. Frequency is how often they go up and down, to kind of put this in simplified terms. The amplitude is how high up the peaks are. There's a slight increase in amplitude, not by a significant amount though. The big key here is that there's an increase in frequency that indicates that there are neural activations, so neurons in your brain that are active in big bursts here and here, which is certainly not the case if we were to look at other regions of the EEG results. These sleep spindles occur exclusively in NREM 2, and it's one of the ways of using a EEG finding to determine what stage of sleep the individual happens to be in. Now to zoom back out, we just went from the white NREM 1 to the red NREM 2. Now we're going to go to this big dark green NREM 3. Non-rapid eye movement 3, or NREM 3, is largely our most unresponsive and deepest stage of sleep by a pretty considerable amount. It's also the stage where the pituitary gland secretes growth hormone, and as we'll see in a later essential task, it is the stage where there are a few very unique sleeping conditions like sleepwalking and sleep talking, even night terrors. The best way to put NREM 3 into context for those of you who have experienced this, and basically everybody has in some capacity, if you ever woke up in the morning, your alarm went off, you think you had a full night's sleep, you feel absolutely dreadful, and you have no idea why. Why do you still feel just incredibly exhausted? You can't explain it. You, in theory, slept for the full amount of time. Likely has to do with the fact that, unfortunately, you woke up in NREM 3. NREM 3 is a nightmare to wake up from, because I don't mean that we're a nightmare literally, we're talking about sleeping here, but it is dreadful to wake up in NREM 3 because you're waking up at a point in which your brain had the least amount of overall brain activity, at least relative to any of the other stages. your brain exhibits less activity when you're sleeping no matter what, but NREM 3 is the least amount of brain activity. So as a result of waking up in NREM 3, it's going to take a little bit longer for your brain to transition back to what it would otherwise be if you were to have woken up in an earlier stage, like NREM 2, for example, or even REM sleep, quite frankly. So NREM 3 is a absolutely dreadful stage to wake up in, and I really want to make this point clear. You should acknowledge that the next time you take a nap. Each sleep cycle is 90 minutes long. As we'll see in just a moment, you actually transition. I'll show you this mnemonic and talk a little bit more about all of this in just a moment, but you transition actually from NREM 1 to 2 to 3, and before you end your first cycle, you actually go back to NREM 2 a second time, which means NREM 3 is going to happen approximately 45 minutes to maybe 60 minutes into your first sleep cycle, which means if you go home and take a nap and set a 1-hour timer and fall asleep basically immediately, 1 hour from the moment you fall asleep, you're actually going to wake up in NREM 3, which means you're going to wake up from your nap in the deepest, most unresponsive stage of sleep, and you're going to feel absolutely exhausted. And oftentimes you're just going to end up taking a much, much, much longer nap. Just to go back to clarify a few other elements of this, if we were to actually classify the brain activity, we would call these delta waves with this really low frequency, meaning how frequently it increases up and down, with much higher amplitude, which is the height of the actual waves themselves. We call these delta waves as a mnemonic. I use the DE in delta and I connect it to the DE in sleep. There are other brain waves that we could be classifying here, but we're going to kind of simplify this just to two. We have alpha waves when we're awake but relaxed, for things like meditation, and then delta waves when we are in deep sleep. DE for delta, DE for deep. The last element of today's concept map is to talk about REM sleep. Then I'm going to zoom out, so don't end the video before I can zoom out and talk about the entirety of this, because there's a few important things going on, because you notice the length of some of these are changing. REM sleep is the last portion of the first 90-minute cycle, and it is the region or the portion of our sleep cycle where we dream. It increases in length as the night progresses, which means if you go to sleep for 8 hours, you spend more time dreaming the longer you sleep. So REM sleep and the quantity of time spent in REM actually increases as we sleep. And if you were to look at an EEG while somebody was in REM, it would actually look somewhat like they were awake. So we call this in many ways, and you wouldn't see this term on the AP exam, but paradoxical sleep, because the person is definitely sleeping, but it kind of looks like they're awake if you look at the brain scan a certain way. So EEG findings can be really interesting when an individual is in REM. And the biggest thing to connect here is that REM sleep is correlated with dreaming. You could technically dream in other stages, but it, by and large, occurs exclusively in REM. There is a very strong belief that you need to reach REM, uninterrupted, full REM cycles, or full REM stages within each cycle, in order to improve memory. Individuals that are interrupted before they reach REM are far less likely to retain information learned the previous day. So there's a very strong belief that REM itself has a valuable asset, or is a valuable asset, in the context of memory consolidation. The last feature of REM is called REM rebound. REM rebound occurs when, usually through sleep deprivation or just simply interrupting your sleep schedule, that for a prolonged period of time you've been lacking REM sleep. Not saying that you never got there, but just relative to other points in your life, you've been lacking REM sleep. And now the very first time that you get a full 8-9 hour night sleep again, you end up spending more time than you would typically in REM. So like, let's say, for example, you went to Florida on vacation and you spent way more time out at the beach, going to whatever it is that you wanted to do down there. Maybe you went to see a Tampa Bay Buccaneers game. You went down there and for a couple weeks, you slept way, way, way less than you would typically. Now, as a result, you get home, you're in your own bed, and the first time you have a real chance to go to sleep, you end up spending way more time in REM, because for the couple weeks that you're on vacation, you never really reached REM regularly. That phenomenon is what we call REM rebound, and it's typically a byproduct of either sleep deprivation or just an interrupted sleep schedule where you stopped allowing yourself to reach REM naturally. As a mnemonic, when I look at the word REM and I look at the word dream, I see the REM, and that's really one of the most important parts. If you were able to connect REM with dream, you should be able to recall some of the key details. All right, I'm going to zoom back out and just take a look at the entirety of your sleep cycle now. Again, Each sleep cycle is a 90-minute interval. So you have here the first 90 minutes. You'll notice I typically try to line these up so that they ended in the middle of a REM cycle. But 90 minutes, 90 minutes, 90 minutes. One of the things to note, NREM 3, which is your deepest stage, actually reduces in length as the night goes on. And by, let's say, your fourth cycle, it usually just goes away. This is the reason why the majority of the time you do not wake up from a full night's sleep absolutely exhausted, because unless you just sort of got unlucky that night before, you're not typically going to wake up in NREM 3, which is great. You never want to wake up in NREM 3, whether that's from a nap or a full night's sleep. So that's a good thing. NREM 3 it decreases in length. REM, on the other hand, actually increases in length. So I made that point in the box above here where my mouse is. The quantity of time that you spend dreaming in REM actually increases from the first to the last time. And then you actually go through NREM 2 twice within each cycle. So you notice we went through it twice here, twice here, twice here. You actually go through it twice, which is why it ends up making up approximately 50% of an overall night's sleep, because you enter into NREM 2 twice during each 90-minute cycle. And then you typically wake up more often than not somewhere between REM and NREM 2. Again, very rare to wake up in NREM 3. There's no more NREM 1 by this point. So you typically wake up somewhere around here, which is good. This is, at least relative to other stages of your night's sleep where you're going to have a reasonable amount of brain activity. So you typically can wake up, roll out of bed, and get your day going without much of an issue.